Hello, everyone. So we're gonna talk in this video. Here's our big idea. We're talking about something called a tangent plane. So we're gonna start with a little intuition about what a tangent plane should be. Then we're gonna figure out a formula for computing a tangent plane. And then we'll do a couple of examples to see how that works. So tangent plane, right? So obviously this should bring to mind a notion we have from single variable calculus, right? Our idea of the tangent line, right? So in single variable calculus, you pick a point, you can use the derivative and find the equation of a tangent line. And usually when I start a class talking about the tangent line, a question I ask is, what is the tangent line? And people usually come up with this idea of touching the curve only once. And I think they mean the right thing, but we've seen examples where this certainly isn't the case. For instance, the idea of a tangent line would look like this, and that clearly touches the curve twice, and it could be touching it over and over and over again, depending on the kind of curve we have. So it's not really the best definition, and a better intuitive definition is the idea it's this line that looks very much like the curve when we zoom in close, right? If we were to, oops, that was the wrong. If we were to zoom in, if we were to zoom in this little box, right, what we'd see is our curve will look more like this, and our tangent line starts to look like, well, I'm not doing a great job of drawing it, but if we keep zooming in, eventually we get something where we get a tangent line and the curve that it's trying to look like being nearly identical, right? And anytime the tangent line exists, at some magnification, you get something that looks like this, where they're almost indistinguishable from each other. So our tangent plane, oh, I just noticed that I wrote tangent line when I meant tangent plane. Our tangent plane is going to play a similar job for us now. We're going to use the tangent plane when we have a surface, right? We've seen these surfaces full of all kinds of curves and bumps and valleys and all these things, and we find at spots, we can find a tangent plane, and the key intuition is that tangent plane looks really, really similar to the surface that we're on at that point. And we can use it for similar kinds of things. We can use it to make approximations, right? Just like we can use tangent lines to make approximations. This is something you all do every day already, whether you know it or not. In our minds, when we picture ourselves on Earth, right? We know that the Earth is round, right? I think we all are aware of this fact. But when you walk somewhere and you think about your path, you imagine yourself walking across a flat surface, right? If you're standing in the middle of a field and you look at how far away something is, you don't consider how much the Earth is bending as you go around that, right? Or when we draw maps, right? When you draw a map, locally, it works really good, even though you're imagining a flat surface that's not actually accurate, right? If you look at, right, let's make this more dramatic. If you look at a little piece of the Earth from the side, right? And you try to draw a map of it, what we typically do is something along the lines of, right, I'm just working in making this picture flat, but you can imagine this all over the, like this red line is a plane and the black line is a sphere, where it's looking at it from the side. What you can do is take a point on the Earth here and draw it right here on your map. Right, a point right here and draw it right here on your map. And when you're close to this point where it's matching perfectly, right? That point is a point on the map and a point on the Earth. And as you go further away, there's a little bit of a difference. When you're close by, there's not much problem, right? Because the distance between these 2 points on the Earth is almost the same as the distance here. However, if you pick a point here and here, right, their distance on this map is much closer than their distance, right? It looks like I've cut that distance by about 1/3 or something like that, right? The further away I get from this point, the more dramatic that, the fact that it's not actually a curved surface, the more dramatic that becomes, the problems with that, the errors in our approximation, right? So this is why a city map isn't distorted, but a world map is highly distorted because there's no perfect way to take something that's a sphere and turn it into something flat like a map, right? But nearby, when you're just doing one city, the differences are negligible, and there's no problem there, right? And so we have no problem mapping the Earth locally, but as soon as we try to draw things globally, we run into all sorts of problems. There's lots of different methods you've probably seen for working them out, and none of them are perfect because there's no way to turn a sphere into a flat surface without distorting it to some level, okay? So the key idea here, though, is the tangent plane is like how you conceptualize the Earth around you. If you're standing in the middle of a football field, you don't think of yourself as standing on the tip of a ball with a slight curve to it. You imagine yourself standing on a flat plane, and you're wrong. You're 100% wrong. If you walk in some direction, right, the horizon, the actual horizontal line is this red one, you're actually curving away from it, but we don't notice because it's so close in approximation. You lose, I don't remember the number, but over miles you lose inches and things like that. And so it's not something we ever notice in our day-to-day experience. All right, let's actually examine this idea of the Earth with a graph before we get into developing the tangent plane. So let's turn on a couple of curves. Here's a little half dome I made that's just made it easier to graph, put these grid lines in for me. And then here's a tangent plane on top of that dome, right? So, and I'm putting in the point where they touch. Right, this is, I know we haven't talked about what a tangent plane is precisely, but I just want to kind of give some intuition here. If I look at this from the side, right, just like that drawing I was doing a moment ago, we see how different the tangent plane is from this sphere, right? But if I zoom into that point, right, as I get closer and closer to that point, we're seeing less and less of the sphere. Right, they're now becoming nearly indistinguishable, right? And so much so that the computer's having a little bit of a tough time graphing them perfectly. And as I look to the side, right, that sphere, which is still curving away, you can just barely see it. You probably can't even see it in the video. I can just barely see it here. There's a little bit of space between them out on the edges, right? But zoomed in, it's no big deal. But of course, as we zoom back out, there's a huge amount of difference between the two of them, right? They're not the same at all. Okay, that's the idea. Let's jump into some of the details, all right? So let's jump over to a whiteboard, work out some details, and then we'll do some examples. All right, so here's the idea. Oops. I'm going to start by drawing a surface. Right, so here's some little piece of a surface. I'm not drawing the whole thing. So let's say this surface is defined by the function f of xy. Let's just give the surface a name. I'll just call it S, defined by this function. And let's put a point on here. I'll call this point P with coordinates x0, y0, and z0. I'm not going to label it on this graph because this graph's about to become fairly ugly. So imagine for a moment that and let's just say about this surface, let's assume that it has, the surface has first partial derivatives that are continuous, okay? So we'll need partial derivatives that are continuous on our surface here, okay? For most of the functions we're going to deal with, that's going to be the case, okay? It's similar to the notion that we have in single variable calculus, right? That you know, the functions generally have tangent lines, but when we run into things like corners or discontinuities, that's also where our derivative doesn't exist. We can't have tangent lines there. We'll have the same thing here. So we're assuming that the first partial derivatives exist, the derivative with respect to x, the derivative with respect to y. And let's imagine now, let's say that I I don't want to, well, I can try to draw this in. Let's try to do this. Let's imagine I take, so remember this point has coordinates x naught, y naught, and z naught. Let's pretend, let's say I intersect this with the plane y equals y naught, right? This is a plane that's just all the points. This is a vertical plane. It's going to be parallel to the xz plane. And it's going to intersect this surface. So let's try to draw what this might look like. So there's my plane. All right, there it's under. And it's going to intersect the plane, right? So I'm going to try to draw it following the contours. And it's going to hit that point because that point has coordinates x naught, y naught, z naught. And this is the plane y equals y naught. Right? Well, that curve defined by the intersection of the plane and the surface has a tangent line in this plane, right? We talked about this in the video about partial derivatives, that we can imagine that there's a tangent line it lives in that plane and it's tangent to the curve defined by those intersections, right? Tangent in the sense that we have in single variable calculus. Because essentially what we've done in this plane, z is a function of only x, because you fix y as a constant. So whatever, you know, if you have the equation z equals x squared plus y squared, if you make y 1, you have z equals x squared plus 1. And now we can, that curve would look like a parabola in that plane. We can do tangent line that lives in that plane, right? So now here, let's be careful here. This tangent line, let's give it the tangent line a name. I'm going to call it R1 of t. This is the tangent line. So remember, this plane is y equals y naught. When we move in the plane, we're moving in the x direction, right? Because everywhere in this plane, y is not changing. Maybe I'll do a quick reminder over here. If this is the x, y, and z axis, if we pick a value of y and do that plane, right, it's going to look like this, right? And so as we move through the plane, we're changing our x coordinates, or if we move up in the plane, we're changing our z coordinates, okay? So that's, I'm not drawing all those axes in here because this gets really confusing, but that's the picture that we have here, okay? So in this plane, what is the equation of the tangent line? Well, I know it's going to go through the point x naught, y naught, z naught. That's the, what we usually call the r naught vector, right? That's a vector pointing at this point. Then we get plus t times a direction vector, okay? Well, let's think about this direction vector. First of all, I know, right, this direction vector is like this in that plane, and in that plane, y does not change. So y is definitely going to be 0, okay? Well, let's just arbitrarily pick 1 for x, right? I know x is changing, so we know that this is going to be non-zero, and I can pick 1 just to make things simple. If I change x by 1, what does z change by? That is exactly the derivative in the x direction of our function at that point. That is precisely what this partial derivative measures. At that point, changing x does what to z? We changed x by 1, z must change by the partial derivative. That's what the tangent line does for us. And so that gives us an equation of that tangent line, okay? Now, let's do the same thing in the y direction. I'll call this R2. It's also going to go through that point. And in the same way, so I don't want to draw it on here. Well, I'll draw it a little bit. Maybe it's going to get ugly. Let's just try. Let's see what happens. Let's make it how about green. So now there's going to be a plane in the opposite direction, or the perpendicular direction, I guess is a better word. Right? And it is also going to intersect this surface and go through this point, because this is the plane x equals x naught, right? And that line of intersection is also going to have a tangent line with a direction vector like this, okay? I guess my drawing doesn't actually go in the positive x and y direction. I didn't, well, that's fine. It's the right idea. This black arrow should be going down if I'm using the traditional orientation. But what's most important is what we work out over here. Same idea, this pink line now, x is not changing. So in the direction vector, there can be no change in x. I can choose y to change by 1 because we know these direction vectors aren't unique, so they're always scalable. So I know the direction vector is changing in the y direction for sure, possibly in the z direction as well, depending on the shape of the surface. And the amount the z direction changes, given a unit change in y, is again given by the derivative with respect to that variable. So there are these two tangent lines to the curve at this point. Okay. Now, for a moment, let's go back to thinking about that thing we started with, the surface of the Earth, right? Imagine playing this game at the North Pole, right? I'm just drawing the top of this, right? I'm slicing it in the x direction, slicing it in the y direction. The intersections would be these lines of, I always forget which one goes up and down, latitude? I think that's right. But anyways, if you drew tangent lines, looking at this from the side, you get these tangent lines that are going completely horizontal, right? They'd be sitting on top of this thing like this. And the notion of the tangent plane would contain both of those lines, right? That's exactly the notion we're going to use over here. And it turns out, if you do this, every plane that intersects, any curve, in fact, that you draw on the surface that goes through that point, its tangent line will live in this plane, right? I'm only doing the curves in the x and y direction, but it can be shown that if you do any curve that lives in this surface that passes through that point, if it has a tangent line at that point, so if it doesn't have some kind of bend or something there, the tangent line will live in the tangent plane if you define the tangent plane to contain both these tangent lines, the red and the pink that we've made up here, okay? So I'm asking you to take a little bit of that on faith. I think this picture of the Earth might make it make a little bit of sense, right? If you imagine driving in any direction over the North Pole, the path you take is like the curve, and you can imagine they're all just going to look like an upside down half circle, or the top of the top half of a circle, and the tangent lines are going to be horizontal. And the tangent plane should sit right on top. Okay, so how do we get a plane to contain these two tangent lines? Well, it must be a plane that goes through this point, and these two vectors, these two direction vectors, must live in both of them. So let me erase some things from this drawing now. Let's erase these planes. Okay, so we're left with the tangent lines, the curves of intersection. Okay. So now what I need is a plane that contains these two tangent lines and goes through this point. So oops, that was not what I meant to do. So it's going to be tricky to draw it, but right, it's going to live on this like that, right? It's going to contain both of these lines, which means it contains these vectors when they're starting at this point, right? Well, now I have two vectors that live in the plane and a point in the plane. We know how to find this plane. We need the normal vector, which can be taken to be the cross product of these two. So what I'm going to do is call this vector here v1, and this vector here v2, right? The direction vectors of r1 and r2. And we can take the normal vector for this tangent plane to be the cross product v1 cross v2. And when we do this, what we end up with is negative the partial in the x direction at this point, negative partial in the y direction at this point, why not, and 1. That's where we end up, okay? That's going to be our normal vector, right? We know this isn't unique, but this is sort of the conventional order to do it in. All right, we're almost there. Now, and I should have said this at the beginning, but I will mention, it's great if you could understand this derivation. A lot of the popular textbooks, including Stewart's calculus book, has a different derivation of this formula that might make more or less sense to you. It's not imperative right now. See if you can work through this and understand it, but we're going to emerge with a really straightforward formula for the tangent plane. Okay, so that's really going to be what we want. But I do hope you can take some time to think about the geometric ideas that I'm attempting to draw here. We'll look at them again with some graphic software in a minute. Okay, we're almost there. We've got a normal vector and we've got a point, so it's easy enough to write down the equation of the plane. It's n dotted with x minus x naught, y minus y naught, z minus z naught is equal to 0, right? That's our plane equation, the normal vector. This is the points x, y, and z that satisfy this equation live in the plane. What does this end up looking like? Negative the partial x derivative at the point, x minus x naught, minus the partial y derivative at that point, y minus y naught, plus z minus z naught equals 0. I want to mention, keep in mind, these are derivatives at a point. These are numbers, right? Same thing up here. This is an actual vector. It's not a vector function. These are numbers right here. So last step, just rearranging this with algebra, I'm going to add the x and y parts to the other side, and we get this plane z minus z naught equals the partial with respect to x at the point, x minus x naught, plus the partial with respect to y at the point, y minus y naught. And there is an equation for the tangent plane to the function at the point P, right? Sometimes people just take this minus z naught, right? And it's not a terrible idea. You can just add it to the other side. Either way is fine, right? So I actually usually like to add to the other side. You get a nice, the tangent plane becomes this function of z, but either way you want to write that equation is perfectly valid, unless instructions are given to do it in one way or another. Okay, so again, I want to point out this is the key takeaway, right? So even if some of the geometry in here gets a little bit iffy, this is a pretty doable formula for the tangent plane. So let's do two quick examples. I'll do one in a little more detail than the other to revisit some of the ideas we talked about, and then one we'll just plow straight through and compute as simply as possible. Let's go over to the graph. Yeah, let's do that. So 1 second. So let's share GeoGebra. Okay, so here is a surface we've seen before. I'll write it out a little bit bigger to make it easier. So we've got this function z equals negative x squared plus 2y squared plus 5. Okay, so let's come up with the tangent plane, but let's do it let's look at the tangent lines in the x and y direction along the way. So first, let's compute some partial derivatives. So the partial z partial x derivative is going to be negative 2x, partial z partial x at the point, oh, sorry, I forgot to say what point we're doing this at. So let's find the tangent plane at the point 1, 1, 2. Okay, so I'll add that to our So yeah, we're finding it at this point, and I'll give this the name P, right? So at point P, the partial with respect to x, I'm just putting in 1 for x, is -2. Let's do the same thing. Find the partial with respect to y. We get -4y. So that means at this point, our partial is -4. Okay. So with that in mind, I can write the equations of the two tangent lines in this x and y directions as follows. So r1 of t, I want it to go through the point 1, 1, 2. This is going to be the one in the x direction. So I want x to be non-zero. The y will not change. And the z is going to change by the amount given by the partial derivative, -2. So let's look at this before we look at the other one. So here is the plane y equals 1, right? So y is on the green axis. We've fixed y to equal 1. So as we look at it in this direction, we see that the intersection between this surface and that plane looks like a parabola. So here, let's actually move it in the more, oh, I know what I can do. Give me 1 second. I'm going to just turn down the opacity of this surface. Maybe this will work, we'll see. So I just want to make it a little easier to see. I can make the red surface a little more see-through. Maybe that helps a little bit. So you can kind of see, I just wanted the orientation to be correct. Now we have our y-axis going, our x-axis going positive to the right, z going positive up, and this grayish shape, the outline, the border between this pinkish color and this grayish blue on the inside is the line of intersection, right? So this I'm trying to trace right there, that's the line of intersection, okay? So if I put in this equation that we just came up with, it is this one, right? We see exactly what we predicted, a tangent line that lives in this plane. Notice it's in the plane and intersects the line of intersection at the curve of intersection at that point, right? We can do a similar thing in the y direction, right? So r2 of t is also going to go through this point. Except now the x coordinate is not going to change, the y coordinate will, and the z coordinate will change by the partial with respect to y, -4. Okay, so now let's look at that. Here is a plane in the x direction, right? So it's perpendicular to the one in the y direction. See, it's at the point 1, 1. I know my orientation is there. Now it's more traditional, the red positive axis to the right. We're looking above. So the first tangent line lived in this plane where y equals 1. The next one is going to live in the plane where x equals 1. And we see it's tangent to the curve of intersection in that direction. So now we have these two lines, tangent to the curves of intersection of these two planes. Let's take these two planes away and notice how these two lines kind of lie flat on the surface. And it's a little easier to imagine there's a single plane that contains both of them, okay? So now, let's write down the formula for the tangent plane. Z equals, so I'll write it as f, the x derivative at the point, the input point 1, 1, and it'll be x minus 1, plus the y derivative at this point, y minus 1, plus z naught, which we know is 2, the z coordinate, right? So remember, just as a reminder, the tangent plane formula we just worked out looks like this, or this is one version of it. And I just put in all the values that we've already computed, okay? So let's now add this plane to our picture, right? So I've got oh, let's do one more thing, sorry. Let's actually put in the values. So I just wrote it symbolically, but we actually computed the x and y derivatives. So z is going to be the x derivative was -2 times x minus 1. The y derivative was -4 times y minus 1 plus 2, okay? And that is the plane that I've graphed here. And as we look around, I think it fits with our expectations in terms of what we think a tangent plane should do. For instance, if I start to zoom in on it, right, as I get closer and closer, now at this very close magnification, the difference, right, we can still see some of the difference between the surface and the plane. Let's get rid of those tangent lines. Let's zoom in just a little bit more. And then take a look at the side, right? We're getting closer and closer where that, so that approximation becomes tighter and tighter. All right, I've done something to make the computer unhappy, so I'm not sure why that shape suddenly appeared. Yeah, and here we can see very nearby. It's, oh, I think I've missed the point now, so it's rendering a little bit oddly because I'm not quite zoomed into the point of intersection. But I think the point is clear, right? These two shapes start to look very, very similar. There we go, as we're very close, right, to that point of intersection. They're almost the same shape, and we can use one to approximate the other. Just like with tangent lines, the difference between them, right, where you see this gap, for instance, up in the upper right corner, that difference is the error, right? When you use an approximation, you're introducing error. That difference is shown right there. Okay, so we're gonna do one more example. I just wanna point out, all we needed to do to complete this problem was compute these derivatives over here and put it into the formula right here, right? I did this to kind of take us through the derivation we did once again and show you it on a nicer graph, but you don't have to do that every time. So let's do one more example where we just go straight to the point. So let's clear all these and do one more. All right, so now here's a different surface. This is a little bit odder of a surface. The formula here is z equals x e to the xy, right? We get a very strange surface. You can see that odd triangle there is probably some kind of confusion the computer's having for some reason at certain points. Maybe if I zoom out a little bit, it disappears, yeah. So that's our surface. Let's find the point, the tangent plane at the point -3, 0. So I'm putting in -3 for x, 0 for y. So that means I've got a -3 times e to the -3 times 0, or -3 times e to the 0, or -3 times 1. So the z value is -3. So in order to compute the tangent plane, remember I'm going to need my two partial derivatives evaluated at this point, and then I plug them into the equation. So I've got the point, I need the partial derivatives. So let's look in the x direction. We're going to have to use a chain rule. We've got two functions of x. So the first one, the function x, has a derivative of 1, and we leave the second function alone. Next, we get the derivative of e to the xy. We leave x there. E to the xy has a derivative of itself, but there's a chain rule. Remember, we think of y like a constant, x times y. The chain rule makes that derivative y. So I get e to the xy plus yx e to the xy. Let's evaluate it at the point -3, at the inputs -3, 0. So putting in 0, we have e to the xy, we get e to the 0, gives me a 1. And then I've got a 0 right out in front of this thing, so the whole second part just disappears. So there's my x derivative. Let's do the y derivative. So now I'm looking at this function and thinking of x as a constant. So the constant x out front, nothing happens. It remains multiplied by e to the xy. The derivative of e to the xy, again, stays the same. So I've got x e to the xy, except I have to do a chain rule again. Now I'm thinking of x as the constant, which means by the chain rule, the derivative of xy is x. I've already got an x out front, so I have an x squared, right? So now I evaluate it at the point -3, 0. So -3 squared is 9. I've got e to the -3 times 0, or 0, which is e to the 0, which is 1, so it's just 9. And so there are my two derivatives, right? And so now I can simply write z is equal to 1 x minus -3, or x plus 3, plus 9 times y minus 0. I'll just write it to make it clear. And then we have plus z naught, right, which is -3, so -3. You can simplify this quite a bit. It becomes x plus 9y. And that would be the equation of the tangent plane, right? So that's in terms of doing things, that's all we have to do. So while there's a ton of interesting and valuable understanding in all the derivations we did, the actual computation of the tangent plane becomes fairly simple. The trickiest part will be the derivatives typically. And so if you can handle the derivatives, you'll be all right. So let's take a look at this as the last thing we do. There's the point. If you notice this point A down here, where this is where we're finding the tangent plane, and here is a graph of the tangent plane. This one is a pretty tricky computation for the computer, so you see it's a little bit sloppy, right? That's not a problem with anything we did. It's just the computer having difficulty. Let's zoom in on this point, on the point A. Right, and again, as I get very, very close to A, there's almost no difference between the surface and the tangent plane, right? There is some difference. You can see at the edges, there's little gaps forming, but at the point A, it's incredibly close. It's going even closer, and I can't make out the difference between them at this resolution, right? So again, that weird funky surface, but at individual points, you can approximate it by a plane that looks very similar. Okay, that is it for this one. We have a few more things to do with the tangent plane. We'll talk about approximating, but we'll do that in some later videos. All right, thanks everybody. I will see you next time.